All right, you guys, we're talking about complex zeros of polynomials. What would make a zero complex? That's something I want you to think about. So first things first, let's make sure we understand our first theorem, that complex zeros occur in conjugate pairs. We've actually talked about this previously. It says that let f of x be a polynomial function that has real coefficients. If a plus bi, so that's a complex zero, where b is not equal to 0, is a zero of the function, the conjugate a minus bi is also a zero of the function. In other words, if we have an imaginary or complex number, it has to come in pairs. Let's take a look at this. Factors of a polynomial. It says here that every polynomial of degree n greater than 0 with real coefficients can be written as the product of linear and quadratic factors with real coefficients, where the quadratic factors have no real zeros. In other words, all it's saying is that if we have a polynomial, and let's say its degree is n, then we can write it as a product of linear factors with real coefficients, where the quadratic factors have no real zeros. Okay, let's start with our first example. It says find a polynomial with real coefficients with the following zeros given. 0, -1, -2i. Now, let's think about that. We're told that the zeros are x equals 0, x equals -1, x equals -2i. Now, right here, this -2i, that's a complex zero. And we just talked about up here that complex zeros come in pairs. They come in conjugate pairs. So instead of 0 minus 2i, we'd have 0 plus 2i. So this polynomial that we're going to write here is going to be of degree 4. There's 4 zeros. Now, let's go ahead and write this function. I'm just going to call it f of x. And I'm going to write each of these as factors. Okay, not bad. All right, next. This is just the same thing as x. So if I just want to distribute that in here, I'm just going to have x squared plus x. And in here, if I were to multiply these out, now let's think about this. This kind of looks like a plus b, a minus b. And if I were to multiply that out, I would think of dots, which is just a squared minus b squared. This is kind of like my thinking cloud related to that. So if I were to multiply this out, that's just going to be the first term squared minus the second term squared. Okay. Well, if I do that, that's just x squared. And then when I square 2i, I'm going to get 4 times -1. So minus 4 times -1. And that gives me plus 4. So now it's just a matter of multiplying these two binomials together. I can start by multiplying x squared to both, so I get x to the 4th plus 4x squared. And then I'm going to multiply the x to both, so that'll be x cubed plus 4x. And just because I'm a little bit of a perfectionist, I'm going to put this in descending order by exponents. And that's my polynomial. Okay, next one. It says find all zeros of the function that, given that 1 plus 3i is 0. Now, knowing that this is a 4th degree polynomial, how many total zeros will we have? That's right, we'll have 4. We're given 1, and that's a complex zero. It has an imaginary number in there. So if I know that x equals 1 plus 3i is a 0, we also know what else is a 0. Nailed it. 1 minus 3i. Very good. Now, if I were to multiply these together as factors, this is fun stuff now. Okay, so if I were to multiply these as factors, well, the first thing that I would want to do is I'd probably rearrange my parentheses so that using my associative property, because now I have x minus 1 plus 3i, x minus 1 minus 3i. Now that reminds me a lot of what I talked about here. It's just a difference of two squares. So that's just going to be x minus 1 squared minus 3i quantity squared, because I don't need this extra parentheses. Okay, well, if I multiply that out, that's not too bad. That's going to be x squared minus 2x plus 1. And then if I if I square the 3i, that's going to be 9 times negative 1, or plus 9. Okay. So we did all of this work to get here just to figure out something that I could long divide this by. This quadratic here consists of 2 of our given zeros, and we need to find the remaining 2. So now I'm going to set this up. I'm going to divide this into the given quadratic. I'm making sure I don't need any placeholders. I think I look good. Yeah, I just said I think I look good. I didn't mean it. I'm in sweats right now. Not going to lie. Okay, now let's have you guys can do this. You've done it before. Let's have you guys long divide this, and your quotient should hopefully reveal our 2 remaining zeros. Go ahead and put me on pause. All right, so when you do your long division, having a remainder of 0 is a good sign. I mean, think about it. We just divided by 2 zeros. So we should get a 0 remainder. And I'm looking at this quotient, and I have x squared minus x minus 6, which is factorable. Right? That's going to give me x minus 3x plus 2. And if I set this equal to 0, I get x equals 3, x equals negative 2. So my zeros, remember we said we had 4, which we do. We have 1 plus 3i, that was given, 1 minus 3i, that was implied, x equals 3, and x equals negative 2, both of which were found. Okay, last example here. We're going to write the following function as a product of factors that are irreducible over the rational, product of factors that are irreducible over the reals, product of linear factors. Basically, as best as I can describe it, we're just going to factor until we can no more. It's going to be really great. Okay? So I'm going to try to color code this as best as I can here for you guys. The first one. So basically, when I factor this, I only want to have rational numbers. And what we know about rational numbers is that they are any kind of number that can be written as an integer over an integer. So to do that, I could factor this if I think about 2 numbers that multiply to negative 36, but add to 9. Okay, we can do that. Maybe I should use a bullet point because that looks like a negative. X squared plus 12, x squared minus 3. Okay, right? Because 12 times negative 3, negative 36, and 12 plus negative 3 would give me 9. So these numbers are rational. Next, let's see if we can continue factoring f of x, but now these numbers are going to be real. Okay, well, if I factor this, it's not going to be real numbers. They would be imaginary. So I have to keep this as is. But I can actually factor x squared minus 3 as x minus square root of 3, x plus square root of 3. Root 3 is not rational, but it is real. So now that was factorable over the reals. Last one here says, I just want to write it as a product of linear factors. each of these need to have a degree of 1. It doesn't specify what kind of numbers we have, so we're going to have to get into the imaginary world. If I set this equal to 0, I get plus or minus I root 12, which can simplify as 4 goes into that, so 2I root 3. So finally, I'm going to write this as x minus 2I root 3, x plus 2I root 3, and then these guys will just carry over. That was my side work here. Okay, so now this is a product of all factors that are linear. In conclusion, in a polynomial with real coefficients, complex roots, and irrational roots, irrational being radicals, they come in their conjugate pairs. Very important.